We are going to take a look now at how we can approximate complicated functions using simpler functions, in particular using polynomials. You might ask why we'd want to use polynomials to approximate other things. There's a few reasons. First, polynomials use simple operations. To evaluate a polynomial, you generally just need to add, subtract, and multiply. Polynomials are also easy to differentiate. We know we can use the straightforward power rule to find the derivative of a polynomial. At the same time, they're also easy to integrate. We can reverse that power rule to find the antiderivative of any given polynomial. You might recall from calculus that the tangent line to a function provides a pretty good approximation of that function near the point where you've drawn the tangent line. This is because for any given x value, both the function and the tangent line have matching y values, and they also have matching slopes. Let's take a look at how we can come up with a formula for this approximation. Since we wish to approximate our function with a linear function, that's a first-degree polynomial. So we're going to call this approximation P1 of x. We know two things about P1 of x. It matches f of x at our given point, the point we've chosen to draw our tangent line at, and it has the same slope as f of x at x equals a. In other words, that means that the point a comma f of a is on our line, and the slope of our line is f prime of a. Using what we know then about how to write the equation of a line, we see that P sub 1 of x has to equal f of a plus f prime of a times x minus a. Our tangent line approximation is pretty good, but it turns out that we can do a quadratic approximation that's even better. We're going to build our quadratic approximation so that its value matches the function value at a, its slope matches the function slope at a, and its concavity matches the function's concavity at a. Let's take a look at how we might do this. To make our three conditions true, first let's start off by, given that it's a second-degree polynomial, we're going to call it P2 of x. And we know that three things have to be true. P2 of a has to equal f of a. P2 prime of a has to equal f prime of a, so that our slopes match. And P2 double prime of a has to equal f double prime of a, so that the concavities match. Given that we already have a first-degree polynomial, let's see what happens when we let P2 of x be P1 of x plus some quadratic piece. In other words, P2 of x is going to equal f of a plus f prime of a times x minus a. That is all P1 plus some constant, we don't know yet, times x minus a squared. And that will be our quadratic piece. Our job now is to find K2 to make our conditions true. Let's check to see if our first two conditions are true. So let's look at P2 of a. P2 of a is going to be f of a plus f prime of a times a minus a. I'm plugging a into my equation, plus k2 times a minus a squared. Well, we've got a bunch of zeros in there, so we do see, in fact, that p2 of a is equal to f of a, and the first of our conditions has been met. Now let's look at p prime of 2, or p2 prime. p2 prime of x, taking the derivative of p2 of x. Well, the derivative of f of a is 0. The derivative of f prime of a times x minus a is just f prime of a. And the derivative of the quadratic piece is going to be 2 times k2 times x minus a. p2 prime of a then equals 0 plus f prime of a plus 2k2 times a minus a. Well, that is just f prime of a, and we see that our second condition has been met. Moving on to our second derivative, we see that p2 double prime of x is going to be 0 plus 0 plus 2k2. We need this p2 double prime of a to equal f double prime of a, but notice that p2 double prime of a is just 2 times k2. So we see that k2 must be f double prime of a all over 2. So now we've figured out what our second degree polynomial must look like. It must be f of a plus f prime of a times x minus a to the first power plus f double prime of a over 2 times x minus a all squared. That meets all three of our conditions. It turns out that if we keep adding more and more terms to our polynomial so that the higher order derivatives match up with our existing function, we can get a better and better approximation. Let's see what happens when we make a third degree polynomial and see if we can establish the pattern that's starting to emerge so that we can then generalize to an nth degree polynomial. Our third degree polynomial p sub 3 of x has to meet these conditions. P sub 3 of a has to equal our function at a. The first derivative has to equal f prime of a. The second derivative has to equal the second derivative of a, so the concavities match. And then we're going to add on the requirement that the third derivatives match up. We'll do what we did before. We'll start off with the assumption that p3 of x is going to be p2 of x plus some cubic piece. This means that p3 of x has to equal f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared plus some new constant, we'll call it k3, times x minus a to the third. Now our job is to find k3 so that our conditions are met. p3 of a is going to equal f of a, and then we're going to get f prime of a times 0, f double prime of a over 2 times 0, and k3 times 0. So in other words, p3 of a equals f of a, and our first condition is met. p3 prime of x is going to be f prime of a, because f of a is constant, so its derivative is 0. Then moving on to the second term, we take the derivative, we get f prime of a. Then we'll take the derivative of the next piece, we'll get 2f double prime of a over 2 times x minus a to the first. And then taking the derivative of the last piece of p3 of x, we get 3 times k3 times x minus a squared. Let's plug in a, and that's going to give us f prime of a, plus we'll get 0 in this piece, so we get plus 0, which is f prime of a. So our second condition is met. Let's look at our second derivative now. P3 double prime of a is going to equal 2 times f prime of a over 2, of course I can cancel those out, plus 6 times k3 times x minus a to the first. That's not P3 of a, that's P3 of x. So P3 of x is that, which is just f double prime of a plus 6 times k3 times x minus a. But of course, if we plug a into that, P3 double prime of a is going to be f double prime of a plus 0. So our third condition is met. We've got one more condition to do. Let's look at the third derivative. P3 triple prime of x is going to equal 6 times k3. P3 double prime of a then is also 6 times k3, and we're going to choose k3 so that this matches f triple prime of a. In other words, k3 has to be f triple prime, the third derivative of f at a, divided by 6. So now we see that P3 of x is f of a plus f prime of a times x minus a. Remember that this piece is P1 of x plus f double prime of a over 2 times x minus a squared. This piece is P2 of x plus our new term here, which is f triple prime of a over 6 times x minus a to the third. Now we can start to see a pattern emerging. It turns out that k sub n, the constant in the nth polynomial, the new constant we have to add on, is always going to equal the nth derivative at a divided by n factorial. In other words, we can establish a rule that says that the nth polynomial, the nth degree polynomial that approximates f, can be given by f of a plus the first derivative over 1 factorial times x minus a plus the second derivative over 2 factorial times x minus a squared plus, and we can continue this pattern on till the nth derivative over n factorial times x minus a to the n. The polynomial we've just constructed is called the nth order Taylor polynomial approximation for the function f of x, centered at x equals a. Its formula is given by p sub n of x is equal to the sum from k equals 0 to n of the kth derivative of f divided by k factorial times the quantity x minus a, all raised to the k power.